Yeah, how are you feeling? In a few hours, that'll be the after party. Woohoo! Yeah, hi, I'm Junda. I'm the co-founder and the CTO of Stellar Network. Our cross-chain bridge has transferred over $14 billion of assets, and our users really love it, fast and secure. And we do believe in the trust-free omni-chain future. So that's why today I'm super excited to share what we have done with some of the zero-knowledge benchmarkings. And I hope all the developers and the people who are interested in this field can learn a little bit from there. Right. Yeah. So in computer science, we are all familiar with all kinds of benchmarks. Some are for CPU spec, and a 3D mark for your graphics card, so you can get your headshots faster than your opponent, and LinPark, right? So the scientific computing, the result is actually used to rank the top 500, HPC, right? And of course, the TPC for database and JetStream for JavaScript WebAssembly. Some may ask, we are still in such an early age of zero knowledge. What's the point of benchmarking, right? And that's exactly what I try to emphasize here, right? I don't want anyone leave this talk and take the wrong impression, right? We are never intended to try to squeeze those 0.1% of performance gains right now. Instead, with this benchmark, what we want to do as a contribution to the community is to make informed decisions. Right? There are so many projects out there, they believe in the technology, they are interested, but they have to build something. And then the first thing they run into is, oh, there are like 20 frameworks out there, which one should I choose, right? So that's exactly what our benchmark tried to achieve here. Say, oh, there are circuits you can write directly. There are compilers or VMs you can use, kind of write higher level languages. Or if your use case is really time critical, you might just have to go with the hardware accelerator directly, right? And on the other side, understand the pros and cons. Again, this is a huge design space. Different frameworks, different algorithms, they choose their own design choices in this space. Sometimes your use case doesn't care about latency, but sometimes your use case might care a lot about proof size, right? So all this you can think about the different variables apply to different frameworks. When we started to do something, I will explain a little bit later on, we also have the same confusion as any kind of new developers come into this field. From the other side, we believe the benchmark will also be very helpful for the framework developers, so who are writing this code to basically provide this APIs or zero-knowledge proving frameworks to the wider community. Why? During our interaction with them, after we have the first initial round of data, almost all of the framework come back to us and say, hey, there's an easy thing we can do to make it quicker, to make the memory footprint like 20% smaller. So I think that's kind of the feedback. Maybe when they were developing this, they didn't say, oh, that might be a shortcut I just take. But then when we kind of present the benchmark to them, they say, hey, there's some low-hanging fruit. I can make the whole framework so much better, right? I think that's kind of the power we believe the benchmark can enable. And of course, for the wider community, we want to have more people rallying behind the zero-knowledge progresses, right? Imagine some news come out and say, hey, there's a new framework in town that's beat all the other frameworks, right? So that kind of make the headline, get more people excited about the progress of the technology. Okay. Now, you might ask, you come from a bridge background. What exactly are you doing with zero knowledge, right? It's actually exactly because we are in this high-risky bridge business. I'm sure everyone has read enough news about multi-sig bridge being broken. Yeah. That's why we say we have to look at something that get rid of this additional trust, right? So that's why we keep talking about trust-free. The only thing you trust is the math and the code, just like Bitcoin since the beginning, right? And if you are a developer right now, all the zero-knowledge based thing is already working, right? We are not just hand-waving, say, oh, the thing will come. It's actually already announced. Everything was published 2 days ago. We have the full, very detailed documentation to explain each step what we are doing with the zero knowledge, and also a very well-written, easy-to-use API inside the SDK. So what you can do exactly is from, say, Ethereum or any other EVM-compatible chain, you can prove the storage value. You can prove the transaction. You can even prove the receipt. So, which of course, for the developers out there, the events, like for example, when you do a swap, a DeFi trade, the final outcome number only lives in the receipt, right? So I think that's kind of the power of it. Of course, because we're coming from a bridge background, this is kind of very trivial to build arbitrary message passing bridge across the chain, right? Again, the power here is that there's no third party in the middle you need to trust. The proof will be generated based on Ethereum, Merkle tree. We will talk a little bit more in detail later, but on a high level, there's no one can even fake or like manipulate the data, because the zero knowledge proving give you the confidence the whole thing is correct, and the layer by layer data that's already built into Ethereum consensus give you the guarantee the data is correct, right? So there is the data integrity is untouched. So, we have been coming to this, talking with both the layer 1, layer 2 rollups as kind of supporting their chains. With Seller, Seabridge, we already have like almost 50 different chains as our partners. But now we're looking more interested into, with this new dimension of data, what we can enable the dApps developer to do, right? So here is one simple example. If you ever done any trade on centralized exchanges, they have VIP program. If you kind of a big average trader, you get a discount in fees. I would say 5 years already passed, and even today, right now, if you go out there, there is not a single DEX can do this. Why? Because the history data is missing. Why the history data is missing? Because it's so expensive to put everything on-chain. So that's why we believe with the storage slot, zero knowledge proof, and also the receipt transaction proof, it's trivially for any DEX to enable, whenever there is a trade come in, unlike today, you always treat them like a brand new address, right? Think about that. That's like unthinkable, unbelievable if you're coming from a Web 2 background, right? Every single transaction happen, even it's your loyal user, you will say, hi, nice to meet you, it's my first time, right? It's actually no, because your on-chain smart contract doesn't know, even though thousands of transactions may already happen, but it's simply not available, right? So that's why we believe the power here by adding this new dimension of history data, and of course, it will be omni-chain, right? It's not just that, if it's on Ethereum, it's only on Ethereum, because we can easily implement a light client in zero knowledge and prove across chain. So like say, even if there some project, they have been very successful on chain A, and now they want to move on to chain B, they don't have to start from scratch, right? They can literally carry some of the thing, again, trust-free to the new chain. Okay? There are many other use cases I don't have enough time to go into, but I hope what I explained earlier will get the developers out there really excited to say, this is kind of can enable completely new use cases. But before we get too excited, we still have to face the question, how do we start to build, right? That's exactly what we did. We said, let's go out there and find all the zero knowledge proving frameworks out there. Let's see, right? Let's see how they perform, how, if it's even doable, because, honestly speaking, last year, this time, I myself is kind of what they call ZK skeptics, right? I saw the papers, I saw some of the numbers, I just don't think it can be practical, right? So it is indeed one small step. We only did SHA-256 hash. The reason being, we choose this, of course, number one, our Brevis will heavily depends on that. Why? Because Ethereum uses it. It's, of course, widely used in many other blockchains. And another interesting factor, if you are in this field, you might heard about like zero knowledge friendly hashes. We choose SHA-256 exactly because it's not friendly. So there's like non-trivial proving work to do. Otherwise, every framework will give you a result within like 10 milliseconds. There's no point to compare, right? And by the way, if you scan, this is a valid QR code, right? It's called Pantheon. If you scan that, it goes to our blog post. Pantheon, that's the benchmark for the zero knowledge proving frameworks. And of course, to be thorough and complete. We vary the input data size, and also to try to keep the variable as small as possible, we write the native circuits using each of the frameworks. Again, this is just the first step. We know there are many exciting, great work being done right now in the field for higher level compilers, IRs, and VMs. That will definitely be our next step. Yeah. And for the hardware, we choose two, right? One is, of course, the Linux server. Mostly the focus is on, focus on the multi-core to look at the parallelization, but per core frequency is lower. And the other is the Mac, because there is another hope that we do not want the proving to be too centralized. Otherwise, everyone will run their prover in AWS. Right? So the decentralized thing will, in the end, will just be a myth. Okay. It's okay you do not understand every word on this. It's also okay if you do not understand any of this on this slide. The high-level takeaway is just like we have gas cars, diesel cars, electric cars, flying cars. It just shows you there are so many different choices out there in this field. The math is getting more and more exciting, and literally every month there will be new paper coming out. Right? So here's the first result. Right? As I mentioned earlier, the complexity in this field, people talking about the number of constraints. That's very critical because it kind of gives you a sense of upper bound, how big the math problem it is. Right? No matter how fast your hardware is, if the problem itself is like 10 times more expensive, you still need to solve a 10 times harder problem. Right? And of course, it's not really very hard to get apple-to-apple comparison. But what we have tried, for the people who are more familiar with all this, and for the same scheme, they could actually generate different number of constraints that kind of even has a 20% difference. That's also a surprise to us, because initially we thought if it's the same, say, R1CS, the result will be similar. But it turns out different framework might have their own secret sauce. And also, of course, if you look at even for the similar plunky ones, some of them with heavy optimization, they can literally achieve like an order of magnitude reduction in complexity. That's very exciting. Right? And now that's the problem with animation. I need to go back to proving time. Yeah, we try our best to do apple-to-apple comparison, and the plot is actually drawn in logarithm scale. So the time, if you go to the top right, is already like in several hundreds of seconds, right? For the bigger size of. Don't worry. Don't try to read. I have a simple one slide summary. And this is the memory consumption. Why we also care about memory consumption is that people talk about decentralized a lot. And there is one fundamental thing. If your hardware requirement is too expensive, naturally it will kind of have this tendency to be more and more centralized. Right? So that's why we say, we would actually like to have the framework even able to run on my Mac, right? MacBook Pro, or even a MacBook Air, or even a Raspberry Pi, right? It's like a low-powered, embedded devices. Okay, this might be one of the most interesting, if you do not remember anything else, this should help you. There is one, obvious winner in terms of speed, but there comes at the trade-off. The proof it generates is not succinct. So that 800 kilobytes, and independent of what size of the data we throw at it. So this actually might still work for some use cases. But for example, for us, for Brevis, we have to verify the final proof on-chain is simply a straight no, right? There is no way we submit like 800 kilobytes of code. I don't even think Ethereum even today support that, right? They claim it's unlimited or like only constrained by the gas limit, but actually there's another much lower limit hard-coded in gas. We found that the hard way. Yeah. And among the Planck frameworks, as I mentioned, the new framework called Boojum from ZK Sync team, with their heavy optimization, it achieves really amazing, both fastest and also with the smallest memory footprint. And for Growth 16, it was kind of the original, or the first batch of the ZK frameworks. The GNARC from Consensus and RapidSnark, they have pretty good parallelization. So that's why we remember in the beginning I mentioned we specifically tested on multi-core architectures. Yeah. And for people using Halo 2, which is, of course, another very popular ZK framework in Rust, it does perform in our test, right? With the lookup table support, it does perform better than alternatives, but it also comes at a but. When the data size is small, the additional setup overhead actually overweighs the performance gain. Yeah. One more minute, I think. I will try to summarize really quickly with this one. You might notice there is a Nova line, but I didn't even mention that because Nova is like similar to a flying car. It's really hard to compare apple to apple with the previous framework. So it's unfair if we just draw the line and call it a day, right? So we actually did something more deep dive with Nova to support its recursive and parallelization. And we actually found something very interesting with Nova, and we are in close contact with the author to kind of figure out. The author himself is also surprised. Right? We didn't expect that. And the per step time keeps going down no matter what, and the final compressed time actually has kind of this stair-like skyrock, right? They basically tell you, do not try to make each Nova step too complicated. Right? So, yeah, I think again, this is absolutely the first step, the beginning of that, and we welcome the entire community. Everything what I just talked about, including Brevis, is open source, on GitHub, with our test circuits, benchmark scripts, and Brevis SDK and documentation, right? So if you're a developer or you are interested to say, hey, I have to deal with some other elliptic curves, feel free to write your own benchmark and share with the community. Yeah, that's all of my talk. Thank you.
Actually, we don't have much time, but you can ask one question. Okay.
Thank you. You now had benchmarks for SHA-256. I myself am trying to start research on benchmarking different ZK EVMs. So I was just wondering what kind of operations would you consider to be the most suitable benchmarks in that direction? Because do you get the question?
Right. So yeah, let's see if I understand your question correctly. So basically, my understanding is that because the EVM we're mostly working on a little bit higher level, it's very hard for you to say directly to evaluate say SHA-256 itself, right?
Yes, because they have this large execution trace.
Right,
so
right.
Wondering.
Yeah, my intuition, right? My intuition for that. So that's why for SHA-256 is more like the building blocks out there. So with circuits, it's like with the circuits Planck, whatever. It's a better benchmark case. But if you say you are anyway looking at a higher level, I would actually suggest go with some concrete use case. Let's say you are proving MPT Ethereum Merkle-Patricia tree, right? That's kind of the whole thing. And it actually will be much easier to write, supposedly using a VM or higher level languages, right? And that's where you compare apple to apple, right? And it's actually more close to a use case, and the developer will be very interested. Because everyone, if they want to do a light client, they have to verify that. Yeah.
Do you think SHA-256 is a good circuit to benchmark against? Because Planckish schemes with lookup tables are going to have an edge just because lookup tables, right?
Yes and no, right? you saw the data.
I did, yes.
That's why I mentioned we didn't just pick one data point and say call it a day, right? Say yeah, Planck wins or no. It's always the reality has more nuances in there. Even the Halo 2 I explained earlier, with lookup table, when the data is larger, it's faster. When the data is small, the lookup table setup overhead actually causes more time. So I think SHA-256, there's no perfect or the ideal benchmark case, right? We picked SHA-256, honestly, number one. We need it in Brevis, right? Like I mentioned, we have to implement a ZK-like client, and for all the slot value verification, we literally have to verify many, many times. Yeah, so there's no way to run it. And two, it is widely used, and people say, yeah, at least we get some idea. It's not the full idea. It's, that's why we welcome the community contribution to get, you can feel free to contribute to other benchmarks or SHA algorithm you think makes more sense to you, right? That's our hope. Okay, thank you.